All right. Hi, everyone. My name is Chris Kang. I am a researcher at Accenture Labs. Accenture Labs is the R&D organization within the larger consulting company, Accenture. And our role within the firm is to investigate, research, and understand cutting-edge technologies and help our clients use those to solve their business problems. So today, I'm going to present to you a framework for managing machine learning models such that it's easier for your data scientists to identify and deploy the most accurate model into your production environment. When I talk about machine learning models, I'm referring to models like linear regression, logistic regression, decision trees, so on and so forth. And I'm sure people in this room are very familiar and have worked with very different types of models. Now, we've worked with clients whose data scientists have trained thousands of those kinds of models, but they couldn't identify the best model to deploy into their production environment because they didn't have a framework. And in the worst case, our clients would actually run stale models in production, and their systems would make business decisions based off of inaccurate results. And so when we looked at the tools in the market to help address this concern, we noticed that technologies were really good at helping you train models in specific environments like Spark or R or Python, but we didn't find a good tool that could work across those environments and train on different types of models. And so there are three sort of higher level requirements that we noticed which these tools weren't satisfying. So one is the complete management of a model's full life cycle. So taking a model from build, train, test to deploy, monitor, redeploy, and retire. Two is staying agnostic to the compute engines that are actually used to run and train your models. And as I mentioned before, it's working across those different types of models and environments so you can support many different types of models. And three is what we call operationalizing the model. That is taking a trained model and actually deploying it into an environment where it's doing something useful, like scoring and predicting against a live stream of data for real-time analytics. As a result of these higher-level requirements at Accenture Labs, we developed our own model management framework. And there are a number of benefits to using our framework. We capture and template any machine learning model that's trained in our environment. And what that means is that your data scientists can easily reuse those templates to train models on different algorithms as well as different hyperparameters very quickly. We also very clearly show you the output of the model as well as all of its associated metadata so that it's easy for your data scientists to compare and contrast different models based on their performance, thereby helping them identify the most accurate model for deployment. And finally, our framework manages and automates the entire lifecycle of a model. And so what we've noticed is that it significantly reduces the complexity required for your data scientists to get a model all the way from build to deployment. And what that allowed for our clients is actually have other users in their organization, like data analysts or business analysts, leverage this framework. And they could actually use the models that were trained by the data scientists and deploy those for their problem use cases. This framework is also really important for IoT. So in IoT use cases, you have sensors in a system, you're collecting lots of data, you want to run machine learning algorithms, and then based off of those results, you actuate or optimize the systems that you're monitoring. And in order to maximize the performance of your system, you need to deploy the most accurate model into your production environment. And so our framework is designed to help you identify and build the most accurate model. I want to take this opportunity to just describe my team and sort of our journey in terms of how we arrived at this problem. So it shouldn't be a surprise to anyone in this room that our clients are dealing with an unprecedented scale of data because of mobile computing, social media, IoT, et cetera. And at Accenture, we've gotten really good at helping our clients deploy batch analytics platforms. So platforms that could help you collect all of that data using something like HDFS, process that data in batch using something like Hadoop MapReduce, and then using different tools to analyze and visualize those results. Now, one of the limitations of that platform is that by the time the data is ready to be queried and analyzed, you've missed real-time data feeds. And so that was the initial problem that our clients had, which my team was responsible for trying to solve. And so people in this room are probably familiar with why the batch process takes a long time, but just to summarize, the time it takes to get your data through an ETL and processing and then finally to a database for serving in a batch type pipeline could take hours or days depending on the amount of data that you have. So our team tried to set out to solve this problem, and our solution was to employ the very well-known Lambda architecture. And again, I'm sure people in this room are familiar with this. So the idea, just to summarize, is that you have a batch, you maintain your batch processing leg, but in addition to the batch process, you take your data, you also send it to a queue, process that data using something like a streaming framework, like Spark Streaming or Storm, store that data in a fast write database like Cassandra. And so now when you go in to do any type of query or analysis, in addition to your historical batch data, you also have your real-time data feeds. So a holistic view of all of your data for machine learning. So at Accenture Labs, we helped our clients deploy this Lambda architecture, and we did it very well. Now, after we did that, our clients asked, great, we can process this data at scale and in real time, now what do I want to do with it? And typically what our clients want to do is actually use machine learning to make that data actionable and useful for their operations. And so now the process looks like this for our clients, and we can take IoT as an example. So in IoT, you have sensors in your system. We help you collect all of that data. We deploy the Lambda architecture, so you use different technologies to process that data in a batch kind of leg as well as a speed leg. And then on your holistic data, you're running machine learning algorithms on some type of compute engine like Spark or R, and then you get predictive results. Now you connect those results to a business workflow so that you can actually do something with it, like remediation, notifications, or in the case of IoT, actually actuating and optimizing the systems that you're monitoring. And we've seen this process for different clients, and I've given two different examples here. So in one, we had an oil and gas producer, and they were collecting data from over hundreds of thousands of sensors in their oil field sites, and we helped them deploy a Lambda architecture that could actually process all of that data at scale and in real time. And they were running over thousands of models for their operations. In another example, we worked with a water utilities client, and what they wanted to do is predict when a failure or a leak would occur in their water distribution network. So they placed sensors along all the pipes in their network. We helped them deploy the architecture to retrieve all of that data from the sensors in real time. And then we wrote and actually deployed some time series models that, based on the data from the sensor, could predict whether or not a leak would occur in the pipes within their distribution network. And so you can see that in this process, you're going to get the most value out of this when you run a really accurate machine learning model. If you have a really inaccurate model, you're going to get really bad results, and that's not what you want. And so the question is, how do you identify the most accurate model for your operations? And so now the process typically looks like this for our clients. It starts with their data scientists. They're looking at their data set. They're selecting different machine learning algorithms as well as initial hyperparameters. Once they have some initial guess as to what they want to train, they take that historical data, they take the machine learning algorithm and the parameters, and then they train that model in some compute engine where the model is actually being fitted to their data. And while that training is running, you're monitoring the execution to ensure that there are no errors occurring, and if there are, you're debugging it to make sure that it's optimally actually training the model you want. And then once you get the model out, you evaluate its performance. with something like accuracy, precision, F1 scores, et cetera. And then what you want to do is iterate on that process, tweak the parameters, or even try different machine learning algorithms, because what you want is the most accurate model. And so for our clients, at the end of this iteration process, they would have thousands or hundreds of models, and their data scientists will be trying to compare those models based on their performance and identify which one is the best. And so the final step to that is what I mentioned earlier, operationalizing that model, so actually making that trained model useful in their production environment. So I want to spend the rest of this talk about this process. The framework that we created at Accenture Labs is to help address the pain points that go along with this sort of pipeline. And I'm going to start by talking about what are the problems or challenges that we saw with our clients when they were trying to do this. So the first thing that we noticed with our clients is that the skills required to go all the way from building a model to deploying it into production requires a significant amount of not only data science skills, but also engineering. So data science at the beginning to identify the algorithms, the parameters, et cetera, but then actually the engineering to code it up and actually get it running in your environment properly. And so typically with our clients, what we saw were resources that like to do the data science and the machine learning and tweaking the models to get more accurate results. And they had other resources who were really good at engineering, and they like to maintain the infrastructure, maintain the compute engines, ensure that the environment was actually training and running their models properly. The second challenge that we saw is, without any type of framework or management around this process, I may be a data scientist in an organization, I'm building models, I'm trying to solve my use case. You yourself may be a data scientist, you're working on interesting problems, you're training lots of models, and I have no visibility into what you're doing. So I have no idea what models you're building, what you're training, the data sets that you're using. And in the best case, what you actually train could possibly be used by me to deploy into my own environment because our use cases are similar. And at the very least, I could look at what you're doing to help inform how I'm building my own models. And so what we noticed is that there was no management around that process. There's no communication between myself, the different data scientists in the organization, and what ultimately happened for our clients is that the machine learning models started to duplicate. So different data scientists were training the same types of models, and then they also started to sprawl because we had no centralized repository to capture all the different models that were being trained in our client environments. The next challenge is referring to what I had alluded to earlier about staying agnostic to the compute engines. So, in your organization, you may have data scientists who really like R. So they're building lots of R models, they're training it, it's working really well, and now comes along a use case where they have a data set that's so large that they can't possibly run that on a single machine with a single R process. So in order to train that model at scale on that size of data, your data scientists now need to pivot to another type of environment, like a distributed framework like Spark. So what we noticed with our clients is that when we tried to get their data scientists to pivot to new environments, the amount of time and effort it took to ramp them up into a different type of framework was significant. And because we had no abstraction around the different types of environments that were being used, it took a lot of effort to get data scientists pivoting to new environments. And the problem only gets exacerbated when you add additional types of modeling environments like Caffe for neural nets, et cetera. And finally, the last challenge we saw is sort of the lack of automation throughout that entire model lifecycle process. So typically, in that diagram I showed you, the build happens very manually, right? The data scientist is looking at the data, they're looking for the algorithms, parameters. But once they're actually ready to get it trained, monitored, deployed, and compared, at that point, there is an opportunity to automate a lot of the steps that occur along the way. So if you take myself as an example, and I want to build a Spark machine learning model, then I pick the algorithm, I code it up, I move it into HDFS or into my cluster, I SSH into that cluster, I open the terminal, I'm running Spark Shell or Spark Submits, and if there are errors that occur, I need to fix that. Maybe my compute engine has some configurations that aren't optimal, and so I have to change that. And then finally, I get my model, evaluate its performance, and then I iterate all over again. And you can see doing that over and over can be very time-consuming. And what we notice with our clients is that they would very much prefer their data scientists to focus on machine learning and getting really accurate models, not spending over half their time doing the engineering and fixing the compute engines and making things work. Okay. And so I'm now going to talk about the framework we created. The purpose, again, is to address those higher level requirements I stated earlier, as well as the challenges that I had just described. And so our framework is an agnostic framework to manage machine learning models at scale. This diagram is showing you the reference architecture. So at the top, you can see runtime environments. That's basically the compute engines like the Spark, R, Python. You have your users on the bottom. In the middle, you have that model management framework. And what we're trying to show you are the features that we think are necessary for a model management framework. So you can see things like an API for programmatic integration, a model repository or a model store, so that you have a centralized repository so that you can understand all the models that are being built in your organization. You have a metadata store that can map the model to metadata about who created that model, when was it created, with what algorithm, what parameters, on what data set, and what schema, et cetera. And finally, the features that you need for automation. So as I discussed earlier, you don't want your data scientists to start SSHing in and doing manual commands. You want a backend service that can translate your intent and just do the work for you. So with a deployment, it's, I want to deploy this model with this type of data on this type of compute engine, and you want the backend service to just do it. And part of that also means is, the backend service should be able to tell you that the model that you want is compatible with the engine that you're trying to train it on.
Question.
Yep.
Is the model store or the trained model store searchable? Like a catalog of sorts?
Based on its metadata, yes.
Okay, so there's metadata wrapper on the model store.
Yeah, so the metadata store should be, based on how you index it, actually searchable, right, based on its fields.
So it will contain all the stuff in the model stores and all that?
So the model store is meant to store the actual physical model object. That itself is not,
So you would search the metadata store?
Yeah, exactly.
Okay, got it.
Yeah. And finally, the last feature is the monitoring service. So actually evaluating the performance of that model as it's running and then reporting that back to the user. Okay. This is a technical architecture that sort of is the parallel to the earlier diagram. And you can see we already have some of those features noted here. So the API, the model metadata store, an actual model store. And so what we've added to that is an actual training service. So the training service is responsible for taking your historical data, combining that with the machine learning algorithm you want, and then producing a trained model. That gets put into the model store. Your prediction service is doing something else. It's taking the trained model out of the model store, running it in your compute engine against a live stream of data that's coming from your message queue, and it's storing the results into your results store. And that's where you can query and analyze the data. And critically, what I wanted to mention here is the idea that we want to stay agnostic to the compute engines. And so that's what the model runtime service is. It's an abstraction to the engines that you want to use. And so what that would look like is for a user to go in through an API call, say, this is the data, this is the model algorithm, this is the engine I want, and then the backend engine takes your intent and then actually performs that work for you. And we've architected that abstraction in such a way that it's extensible. And I think that's really critical. So if you came to us with an environment that we've never seen before, we would do the work to wrap all the necessary code to get models trained and deployed in that environment as its own microservice. And then we would plug that microservice into the backend. And so at that point, what you could do is go into the framework, and then through the same API call, train and run your models through that backend. And some of the example technologies, just for reference, that we've used. So in the historical data storage, we've worked with things like HDFS, S3. In the online message queue, we've used things like Amazon Kinesis, Apache Kafka. We've used the S3 for the model store. For the results store, we've used fast-write databases like Cassandra, Amazon Dynamo. We've built APIs in Node and some of the microservices in Python as well. OK. So are there any questions before I go into the demo? It's probably the most fun part. OK, yes?
You didn't talk about auditing. So in many applications, there's a need to go back and I scored this piece of information against that version of the model.
Yeah, exactly.
Is that baked into this?
So we continue to work at extending this platform to make it more production ready. And so I think those are one of the things that we want to connect all the pieces into. So by capturing all the metadata, like the version of the model, the history of how it was trained, we can add that auditing type of feature. We haven't built that yet, but we have that in mind, for sure.
Thank you.
Yeah. Yes.
Can you please explain me on the previous, how the Lambda architecture is useful in this particular framework?
Yeah. So with respect to machine learning models, the idea would be that you can train your models on that batch leg. So you have your historical data for training your model, but then you can actually deploy it to the real-time data feeds. And so I'll actually show you an example where I'm actually doing that in the demo. Yes?
It's currently used in production, for example, in the labs, because it seems like it's an idea, or?
That's a good question. So with labs, we have, what I'm going to demonstrate to you actually right now is a prototype. And so we actually have deployed that for different clients. We are in the process of actually making it a production platform of its own within Accenture as its own offering. And that's happening right now.
Will that be open source?
Great question. I don't know. We'll see. Yes?
How do you store your model meta store? Like, do you store your model in a raw format, or do you serialize it before storing into a meta store?
We serialize the model object, but any metadata that's updated is just like fields, metadata, like a document store. You can add different types of fields like version.
R, or in a Python or something?
I'm sorry, say that again?
So your models are written in R or Python?
We've used Spark. We've done it with Python, and we've actually done it with Caffe as well. So again, the idea is that you can extend it to different environments. So R should work as well. Okay. So I'm going to go ahead and go into the demo now. Great. So as I mentioned earlier, again, this is on its way to becoming its own production platform. But what I'm presenting you here is a prototype that we created at Accenture Labs almost a year ago. And I always like to start this demo by saying we're not trying to trivialize the machine learning process. So we're not just giving you like 5 to 10 algorithms that you have to use. The whole idea, the whole point is that you can load your own algorithms to actually run. And so I've actually loaded through the API call already my own machine learning model. It's a time series model, and you'll get to see that shortly. So pretend I'm a data scientist. I'm going in. This is my experiments page. And so you can already see that we're showing you transparently all the different types of models that we have, right, including all of its metadata. And so what I'm going to do now is actually train and add my own model. So if I add my own model, to the question earlier about how does that Lambda architecture come into play, this is where we select the historical data store for your batch data, right? And so in this example, I'm just going to pick a flat file in S3, just for simplicity. Going to pick a flat file, call this model Hadoop. Cool. And so typically in a machine learning scenario, you're trying to select input features for target features. Now I realize that that's not always the case, right? You have unsupervised learning, you don't have a target. But just bear in mind that's just an example. And so with this, my input is time and temperature. I'm running a time series model, and I actually want to predict the value of temperature in the future. So these are my inputs and outputs. Go in. And here is where we already have a number of different algorithms. But again, the whole idea is not to restrict you to 5 or 10 that we have. The time series model is something that I actually created and uploaded. So this is a time series model. And you can see these are the hyperparameters or the attributes of that model that you can change and tweak. So I'm just going to select some default values here. Next. If you scroll to the bottom, you can see this is that object. But now, at this point, we've only collected metadata. Nothing has happened. I haven't trained the model. I have no real output. And so what I want to do now is actually take the algorithm, the parameters, the data set, and actually fit that model in my compute engine. And so when I hit train, this is where we try to show you that extensibility, the idea of that, right? So here I can select Spark on an on-premise Hadoop Yarn cluster or Spark and EMR. This is just an example at the time. We've actually extended this to work with things like Python as well as Caffe. But you can see the idea is that you should be able to, as a user, just select the engine that you want, right? You don't have to go into the cluster and actually like work with each of these individually and separately. So I'm just going to select Hadoop here, and then this will actually make an API call. The backend services understands your intent, does all the work to take that data, take the algorithm, and start running that and training that in your compute engine, and it'll output a trained model. And so at the top here, you can see these are models I've already trained. And so now what you want to do, as I mentioned, is operationalize that model, right? So take the trained model and actually deploy it to an environment where it's doing something useful. And so this is the deploy action. And in deploy, it actually works very similarly, and you still select the compute engine that you want. The difference being is that the model is being pushed to a production environment where it's scoring against a live stream of data. And so that's the same for deploy. Now, what I want to show you next is sort of the last mile. So I've already trained and deployed a model through this framework, and I want to show you what it's actually doing, something useful. So this, let's see. So this is another demo that we created for a client. This is supposed to emulate an oil and gas scenario, and in this case, they have oil wells in their sites, and what they want to do is predict when a certain tank is going to overflow based on its current rate of fill. So, I wrote the model. It's really simple, right? You just take a rate calculation, project it forward in time. But the idea is that I trained that model, I deployed it using my framework, and after deploying it, I should see the results here, something actionable. And so when you load this, hopefully this works, great. So you can see the blue is the raw data, so that's the current level of the tank, and we're measuring the rate of fill. And the model is outputting the predictions, as you can see in the orange points. Right? Simple model, but the idea, again, is that we've actually deployed it, and it's doing something useful for our clients. Okay? Awesome. Okay. So I'm going to just summarize now. I presented to you, again, a framework for model management. We've captured a lot of features, but again, it's to address a lot of the pain points that go along with training and deploying machine learning models for a production environment. The key differentiator that I believe is really staying agnostic to those compute engines and then automating the processes to get the models deployed in that environment. And that's that first feature. We again build a library of your machine learning algorithms. We're not trying to restrict you to 5 or 10. You can actually load your own, and so that library should grow as your organization uses this. We capture the metadata about those models, so they are searchable. We work with heterogeneous data stores, as you saw earlier. The S3, Redshift, HDFS for pulling data from the historical data store. What we call champion challenger, which is just comparing and contrasting the models to find the most accurate, capturing the idea of the batch processing as well as the real time, the Lambda architecture, and then using and storing the results of your deployed model for predictive results. And ultimately, this is an invention that we created at Accenture Labs. It's enabled for real-time analytics. We try and cover lots of different types of environments, and that's really useful for us because our clients are very wide-ranging, and they're working with lots of different types of environments and models. We're simplifying that process with automation. We let other users in our client organizations actually leverage this framework, and finally, we tackle IoT use cases, which are very prominent with our clients. So that's the end of my presentation. Thank you for listening, and I can take any questions that you may have. Yeah.
When you talk about the execution that is happening for the model, right?
Yes.
Are you using H2O or behind the scenes?
No, we're not. We're using our own backend service that we've coded up, essentially.
Are you parallelizing your model using smart analytics or just trying to understand?
Yeah, so it's up to the user, right? So if they want to select Spark as their engine because they want to do some type of parallel or distributed at-scale modeling, then yes, they can use Spark. But if they don't, and they want to use Python scikit-learn, or they have a video analytics use case and they want to use Caffe or a neural net model, something entirely different, then they can do that too. That's the idea. Yes.
You moved from model training to model deployment. Where do you evaluate the model before you push it to production?
So when you train that model, I didn't show it in the demo, it actually returns to you the performance. So things like you would specify what the metric that you want, so like accuracy or F1. And so we would capture that metric, store it in the metadata store, and actually show it to the user. We don't have that in the demo, but that's the idea. Yeah. Yes?
Let's say I have a customized model that I train with Spark. How do I import it to this framework?
So we have an API where you would upload, in the case of Spark, like your own jar file, essentially.
Jar file.
Yeah.
So I have to somehow put all my model into a jar file.
Yes, yes. You need your own code that actually trains that model with the specific machine learning algorithm that you need, right, that you want. Yeah. Yes?
I have one question. So you mentioned you have two execution models. One is batch, one is real time.
Yeah.
And is it transparent to the customers, or user have to make a choice which one you want to use?
Yeah, so when we showed you that demo, I think the batch is clearly captured, right? Because you're selecting the historical data store that you want. But when you want to do the real-time deployment, we're not showing you like the different types of streams that you have, for example. But we could show that to the user and say, these are the streams that are feeding in real-time data, and select the stream as well as the topic that you want. And that would very clearly indicate to the user you are deploying a model against this certain specific real-time stream for the real-time updates. Does that answer the question?
Yeah. So another one is about the model. So assume you have some model that already exists in the system.
Okay.
Do you have any discovery mechanism that help the data scientists to find the existing one, such that they don't miss the existing and use a new model themselves?
Say the last part again, sorry. So they have the model, so you have models, but you can't find them.
Yeah, do you have any discovery mechanism in this framework to find the existing models?
So if you use our framework, we've captured the model, right? So we have it in the metadata store. We know who created it at what time, and we know its location. But if what you're saying is that you've created models not using this framework, then you would have to write your own processes to identify and find those models. Like we don't run like this offline process to like go into your environment, find the models, and then do some type of like transfer into our framework. We don't have that yet. Yes.
When you train your model, if the data set size is different, how do you choose the backup cluster size?
The cluster size?
Yeah, how do you choose your training cluster?
So the idea would be that we want to abstract the data scientists away from that. We don't want you to worry about like selecting the number of executors you need in your computation. So we would prefer that the backend engineers would actually fine-tune that based on the models and how they're performing in the cluster.
Your system already has this built-in.
Yeah, basically it's preset, right? And so your engineers in the backend are going to be tuning it based on how things are actually running. But what we don't want is our data scientists to upfront be like, hey, this is the exact setup of the cluster that I want. We don't have that level of granularity yet. Yes.
You mentioned about the champion, challenger, the two models. So in the Lambda architecture, is the champion in the real-time field and the challenger in the batch field, or how those two models, where do they decide?
In the simple example, it's actually just, you train models on batch. So all your models are trained on some type of batch historical data. And that's where you do a champion challenger, comparing and contrasting the models to find the most accurate one. That most accurate one goes against the real-time data stream. Yeah. OK. Oh, sorry, yeah.
How can you decide the best performance model? You just trial and error?
So I mentioned earlier that we didn't show it in the demo, but you would specify the metric that you want to evaluate your model by. So there's all sorts of metrics, right? Like F1, log loss, et cetera. That's what you would use, essentially.
You try one model, you got some performance.
Yeah.
And you try another model, you compare the performance, and you decide that which one is better.
Yeah, exactly.
Keep trial and error.
Yeah, more or less. Yeah. OK. Thank you, everyone.